And I'm going to be doing the magnetic breaking with Faraday lab. So first, the rules of the game. Faraday's law, it's changing magnetic flux makes an EMF, which is that first formula. And then Lenz's rule says that the induced current fights that change, which means that nature hates surprises. A following bar magnet is a little dipole. Its field lines bulge, so flux through each aluminum ring changes every millisecond, and those rings light up with eddy currents. Their own magnetic field opposes the magnet's motion, giving us that upward force that drags the big descent. So the big idea is converting gravitational potential energy straight into Joule heating in the tube. No stickiness, no hidden magnets, just electrodynamics. So here's the low-tech rig, a 27 centimeter roll of Reynolds aluminum foil taped into a tube, inner radius 1.5 centimeters, wall 2 centimeters thick, magnets 23 grams, dipole moment 1.2 amp times meter squared, and then the iPhone was at 240 frames per second times the drop. So 5 drops later, an average of 2.41 plus or minus 0.04 seconds from top to bottom. Control drop through air 0.235 seconds. So braking multiplies fall time by 10. Alright, so here's the computational model in GlowScript. So I sliced the tube into 54 rings, and in the code I1 fed in geometry plus mu, 2 dipole B spits out the point dipole B field, 3 get analytic d5 or dt for each ring as the magnet moves, 4 I equals negative d5 over dt over r gives current, which is Faraday lens, 5 current loop fields F equals IL times B, opposite force hits the magnet, 6 add gravity for F net, 7 Euler-Cromer updates position and velocity every 1 millisecond, and 8 graph velocity versus time in color rings, red for clockwise and blue for counterclockwise. But there were some assumptions. So one was that the rings don't touch each other. The other one was that magnet equals point dipole, and the other one was aluminum resistivity uniform. Alright, so this is model versus reality. So my simulation predicts 2.32 seconds in tube. That's 4% shy of my 2.41 second average, which is a solid agreement. The small gap, that's the edge field fringing at the tube ends. A little wobble when I drop it, I ignore air drag. But the curve shape matches quick ramp near terminal crawl and then free fall again. So here's the what ifs and takeaways. So let's play what if. So zero resistivity, think superconductor. D5 or DT stays the same, but R approaches zero, so current approaches infinity. And then magnetic force could balance weight, so the magnet would literally levitate. And then for slots or holes in the tube, break closed loops would mean no eddy currents, which would mean magnet drops at almost G again. So the big takeaway is that Faraday plus Lenz link changing magnetic fields to real world motion, turning a cheap foil roll into a physics demo that feels like sci-fi. Thanks for watching, and yeah.